I'm going to talk today and in recitation on Friday about computational geometry, which is something we haven't talked about essentially. There's a little bit of geometry in the quiz, but I want to tell you about computational geometry. It's a neat field. The general statement of the field is you want some algorithms for solving geometric problems. Okay, so it's very hard to define this term. And anything that you want to do geometrically on a computer, that's sort of computational geometry. Okay, so computational geometry comes up all over the place, like in computer graphics, simulation of physics, models, and so on. Geometry comes up all over the place, and it's a natural target for applying our algorithms. Okay, so today in particular we'll develop a data structure for geometric problems. Before we jump into that, I want to give you a very simple picture of computational geometry. What sort of structures you might be interested in. Okay, so maybe the simplest geometric object is a point. Hope you all agree. Point here, it's on the plane, but it could be in some other dimension. Maybe the next simplest thing, well, is a line segment. Okay, between 2 points. Maybe a little simpler than that is a line. So a line is infinite in both dimensions. Okay, sometimes people say line and they mean line segment, but this is a common distinction. And you're given some set of points or some set of line segments or whatever. You want to do some computation on them. So that's very rough overview. But here are some things. Here are some basic structures in computational geometry that are interesting to try to compute, and also, once you have them, useful for building other things. Okay, so a simple kind of input is a point set, okay, which is just a set of points. Usually I'll be talking about the plane. If you're given a point set, maybe one thing that you'll ask for is maybe the same point set, I'm not sure. One structure you might want is something called a polygon. Okay, I think you can imagine what a polygon is. It's a closed loop that doesn't intersect itself. Okay, I won't talk about polygons, but they're a key idea. You'll probably run up into them in many places in the future, so I thought I would mention them. Often you're given a polygon, you want to do something with it. Either that or you're given a point set. So let's suppose we're given a point set. Another thing we might ask for is a triangulation. So triangulation is a collection of triangles between those points. Okay? These are all easy ideas. The hard part is to do these sorts of computations. Find a triangulation given a set of points. Okay, there are lots of algorithms for doing that. You can do it in n log n time. This is an important problem in a lot of contexts. It's a particular form of meshing. Okay, so you have some domain. You want to, say, simulate fluid flow through your domain. Then you'll throw a bunch of points into it. Those are sort of particles of water that are floating through the domain. You want to mesh it so that you can figure out who's next to whom and this sort of thing and do local computation. That's called the finite element method. You may see that at some point. And so triangulations are an important problem there. Another problem I'll mention, and you'll see it in recitation on Friday, is finding the convex hull. So if you're given a set of points, this is the convex hull. It's sort of the smallest polygon that contains all the points. Okay, it's a particular form of this problem. All right, that is the shortest summary I could give about computational geometry. If you want to know more about them, I brought along some good reference books. Book by Joe O'Rourke, who's at Smith College, about 2 hours from here, and this book by 3 Marks and an Ottfried, Mark de Berg, Mark van Creveld, Mark Overmars, both called Computational Geometry. Good references. Today I want to talk about 2 structures, and one in particular, which is some of the more algorithmic problems. Okay, so I'll spend most of my time talking about something called orthogonal range searching. Which is basically about point sets and asking questions about point sets. Okay, so it's one of the simplest forms of problems. Let's say you have n points in d dimensions. Okay, this is very hard to visualize because d-dimensional space is potentially really big. But this actually is rather natural. It comes up in a lot of settings. If you have any sort of database, and each record in your database has several fields, and so that's inherently high dimensional. Okay, so you can think of this as a database with n records, each with d fields. Okay, and so for example, let's say you had a restaurant database. Okay, you have a bunch of restaurants. Those are your records. Each restaurant has, how good it is, how many stars it has on some ranking, how much it costs for an average meal. Okay, those are 2 dimensions. You might throw in the latitude and longitude of the restaurant, so you actually know where it is. Okay, so that's already 4-dimensional, and then I can't draw it anymore. But it's very easy to get high-dimensional problems, and you want to know something about this set of points. So what sort of things? Let me draw some examples. In 2D, you know what a point set looks like. Okay, that's about my limit. I can also try to draw a 3D point set. It looks something like this. Right? There, now it's in 3D. Okay, it looks roughly the same, but imagine these points are in space. And the sorts of things you want to know, so what kind of queries do we want to do on these point sets? Okay, it's called orthogonal range searching. Orthogonal means, I guess, horizontal and vertical. That's one definition. George was telling me that ortho means right. Right? So correct. But this means right angles. Okay, so everything meets at right angles. So for example, suppose I give you some rectangle. Then a natural thing you might ask is, what are all the points in that rectangle? Okay, so in 2D, maybe this is, what are all the restaurants in this region? Or with this x-coordinate and this, in 3D, it's maybe easier to form interesting queries. So in 3D, you have some kind of box. You want to know all the points in that box. So maybe I want the set of restaurants that's in this rectangular region, and the price range is somewhere in here, okay, in the z dimension. So that's a very simple kind of database query. It comes up all the time. It's probably one of the most important database queries. And the question is how to solve it. So let me write this more formally. Your query is some axis-aligned box, okay, in d dimensions. But most of the time, we'll be thinking about 2D because that's a lot easier to picture. And then it's just a rectangle. Okay, but it's an axis-aligned rectangle. And what you'd like to do is report on all the points in that box. And there are several things you might mean by the word report. Some examples are, is there anything in there? Okay, Okay, are there any points in this box, or is it empty? Okay, once you know that there are some points in there, maybe you want to know how many there are. Okay, and then once you know how many there are, maybe you want to know what they are. So let's say list them. Okay, these are sort of in increasing difficulty. And we'll talk mostly about listing them, but it turns out we'll be able to solve all of these queries efficiently. I mean, this is the most powerful query. The trouble is, if there are a lot of points in the box that you're looking at, this could take a long time, whereas these you can do faster. Okay, so we'll be able to do all of these fast. That's our goal. Well, if I just give you a set of points and I give you a box, what's an algorithm for finding all the points in the box? It's actually pretty easy. Yeah?
Go through each one and see if it's between the x-coordinates and the y-coordinates.
Right, go through each point and see whether it's between the x-coordinates and the y-coordinates. Okay, so there's sort of, let's call this a one-shot problem. So what's the running time of that algorithm? If I go through every point, that's order n. And then for each one, I have to check whether it's in the right bound. So just a constant. Well, depends on what dimension you're working in. Okay, if you want to be careful, it's n times d. But you're right. I'll pretty much assume today that d is a constant. Okay, good. So 2 or 3 or 5 dimensions. I call this the one-shot problem because it's for the problem where I give you the set of points and one rectangle that I'm interested in. Okay, but what I really care about is I give you a set of points. You know, the set of restaurants in Massachusetts doesn't change too often. Okay, maybe more often than you'd like, but relatively infrequently. But I have lots of queries I want to know. You know, someone goes up with your cell phone, and you press a button. You say, OK, I'm here. What's the nearest restaurant that has this specifications? Right? There are a lot of people with a lot of cell phones. You walk down Boston, half the people you see are on their cell phone. Right? So there are lots of queries. And the point set isn't changing very much. Okay, so this is called, I guess, a static data structure. What I want to do is pre-process the points into a static data structure, and then solve many queries. Okay, so this is a data structures problem, except that it's not really, I don't care whether what we have is a dynamic set. Okay? I'm willing to assume that the point set we have doesn't change. You can do all you want so that you make these queries go really fast per query, because I'm interested in a lot of queries on this particular data set. Okay? And in particular, that's what you're asked to do in the second problem on problem set 6, is it? Whatever the current one is. OK, but let's start out. So we're going to solve that. And let's start out with one dimension. So one dimension is a lot easier to handle. It's not really geometric, so but we need it as a preliminary step. So one dimension, your points are somewhere along the real line. Okay, maybe somewhere like there. Okay, and a query, what's a query what's an orthogonal range query in one dimension? This is something we saw in last lecture. Yeah, an interval, right? So I give you some minimum x and maximum x coordinate. I mean, there's only one axis, the x-axis. The query is just an interval. So how should we solve? I mean, what's a way that we know how to solve orthogonal range queries in one dimension? Yeah. Use interval trees, right? So one approach is to use interval trees. Okay, we know how to do interval trees. It's sort of overkill. So how do I make this set of points into reasonable input for an interval tree? People are starting to wake up. It's early in the morning, I know. Yeah?
Intervals of length 0.
Intervals of length 0, right. Okay, remember, interval trees deal with sets of intervals. Okay, points are not intervals in the strict sense that I want to use, depending on your exact terminology. So I'll replace each point with an interval that starts at that point and ends at that point. Okay, take any point x, map it to the interval xx. Okay, then I can use interval trees, and the query with an interval tree is I give you another interval. What intervals overlap it? And that's exactly a range query. Okay, but it's a bit overkill, because these are rather trivial intervals. So this results in a dynamic data structure. I'll abbreviate data structure DS. That supports queries reasonably fast. So who remembers the running time if we want to find all of the intervals that overlap the given interval for interval trees? Yeah? K log n. Where k is the number of intervals, or the number of points we get. So k is the size of the answer. Okay, that's reasonable, but it's not as fast as we could do. So I mentioned it's possible to get k plus log n. So that's what we'll do today. So to get a dynamic data structure, it does k plus log n time, which is optimal. So any ideas on how another approach, maybe even a simpler approach, to solve this problem in one dimension? So this was easy because it used something we already knew. But if you go back to before this course, right, there's an easy way to solve this problem. Well, maybe like the first lecture. Silence, yeah. Sort the points. Binary search, right. Good. You all remember that, right? Way back. Sort the points and use binary search. Okay, there's just one dimension we're worrying about. We can sort them. And if we want to solve this range query, we want all the points between here and here, we can binary search for this point, and we can binary search for this point, and then just take all the points in between. Okay, so that gives us, this is a static data structure. Okay, because if we want to insert and delete points, it gets a little trickier. Right, it's hard to insert in the middle of a sorted list. But it runs faster, and it's really simple. what's the running time of this algorithm for range searching? Okay, this is a little tricky, perhaps, because there are multiple issues going on. Any ideas? So what are we doing? We're sorting the points, and we're using binary search. So how many times do I sort the points? Once, right? So this is the pre-processing step. Okay, and that takes n log n time. How many times do I binary search? Twice. Except twice for every time I do a query. Okay, so these are really different. I mean, yeah, I only do this once, and I only do this twice. But I do this once every time the set of points change. And I'm assuming that the points never change. I do binary search twice every time I want to know the points in a range. Okay, so the query time is log n. And the pre-processing time is n log n. Okay, this is probably obvious, but I want to rub in what kind of data structure we want here. Okay, so that's pretty good. And I said I wanted a static data structure. And, sorry, log n. Log n is to do the binary search. I'll probably also need k to write down the answers. Right, once I know where the answers are, I have to output them. If there are k answers, it'll take k plus log n time. But notice I can do these other things in just logarithmic time. I can tell you whether there are any points in that array in a range in order log n time. I can tell you how many there are in order log n time just by subtracting the indices. Okay? So that's cool. Okay, but that was too easy. We want a more complicated data structure to solve this problem. Okay, why? Well, this is sort of so special. It only works in the static case and only works in the one-dimensional case. Okay, but there's something that's similar, a little more complicated, that will generalize to higher dimensions. Okay, so that's what we want. The idea is to use a balanced search tree. Okay, you thought maybe you'd never see the end of balanced binary search trees, but they're a central idea. We'll use it all the time. Okay, so sorry. But it's very easy to use them. We just know everything runs in logarithmic time. Okay, so it's not hard to use them. It's just maybe hard to implement them. All right. But I'm going to use balanced binary search trees in a new way. So I'm going to be a little bit different here. Let me draw a tree. So normally, with binary search trees, we store something at every node. Right? Seems reasonable. And then we worry about keeping them balanced so that there's only logarithmic height. Okay, but let's take this data set. So humans are very bad at generating random numbers. So I wrote down some random numbers ahead of time. So suppose I give you these numbers, and I would like a one-dimensional range query search structure for searching among these points. Okay, ignore the fact that I've drawn them a little bit out of kilter vertically. Okay. I could put each of these points in a node of the binary search tree. But what I'm going to do instead is only put them in the leaves. So that's the new organization. Okay, and then I build a tree above them. So let's suppose my red-black tree or whatever looks like this. And these are the leaves. These are the nils hanging off. Okay, but now, instead of putting nil there, I'm actually going to put some data. And these nodes, I don't really care too much what I put in them. But what should I put in them? Okay, if I put all the data down in the leaves, what should go in this node? Three? Three's good. Yeah, anything between 1 and 6. Okay, so just to be canonical, I'll use 1, which is the smallest thing that I could put in there. Okay, so I'll put 6 here and 8 here. What I want is the binary search tree property. Everything in here should be smaller than this node, and everything in the right subtree should be larger than this node. So that's what I'll do. So all the non-leaf nodes, the internal nodes, are storing the smallest thing that would respect the binary search tree property, or the search tree property. So that's the maximum point in the left subtree. Okay, so each of these nodes is storing the max in here. So that's easy enough. Now the question is, how do I support range queries? So let's suppose I do a range query on the interval 7, 41. Okay, that's somewhere down here. So what I want are these leaves. Okay, 8, 12, 14, 17, 26, 35, 41. And one way to represent those leaves is to take this leaf, take this entire subtree, take this subtree, and take this subtree. Okay, so that's the key property of this tree organization that we get. Okay, that we can say, well, I don't have to say 12, 14, 17. I can just say that subtree rooted at 14. Okay, if I give you this node, and this node, and this node, and this node, you can figure out what the answer is. Okay? And that'll be important for going to higher dimensions. That's the idea. So let me show you why this is good. So these structures are called one-dimensional range trees. And in general, when you do a range query, you start at the root of the tree, and you start working your way down. And it could be, you discover, that the interval you care about down here only involves nodes in the left subtree. Okay, don't draw this in yet. I'm going to erase it. Okay, it could be that everyone to the right is irrelevant. Okay, so I can throw away the right subtree. Just look at the left subtree. Okay, this could go on for a while. It could be now, from this node, only the right subtree is relevant for a while. And then only the left subtree is relevant. And then at some point, you discover that both the left and the right subtree have nodes that you care about, have leaves that are in your range. Okay, I'll write down the code to do all this in a moment. But at that point, you split. Okay, so this is called the split node. Okay. So we know that there are some interesting elements in this subtree, and there are some interesting elements in this subtree. But not necessarily all of the elements here are within our range. So we want to know which ones are in our range. So it could be, for example, from here, everyone in the right subtree could be in the appropriate range, okay, like it looks like here. But the left subtree, maybe some are in and some are not. Okay, so maybe here we have to go right for some time before we discover a subtree that's entirely within the range. And in fact, maybe that's all that's in the range that we're looking for. Okay, so let me erase this interval. Okay, on the right side, you get some similar pictures. So maybe it looks like this. So this is the interval we care about, the range we're looking for. And a particular picture of what might be going on is that these 6 subtrees are all the elements we care about. So all of these leaves are in the range that we're looking for, and no more. Okay, everything outside these subtrees is are not in the range. Okay, the question is, how many of these subtrees could there be? I claim that this is going to help us a lot. Okay, the worst is, I guess, that there are k subtrees, one for every element in the answer. But it's not always so bad. How many subtrees can we have? Well, maybe you should think about it. I don't need the answer quite yet, so why don't I give you the pseudocode for what's going on in this range query? Okay, because all of this that I'm talking about is not in the text. So to be explicit, I will give you the pseudocode. So this code will search in this binary search tree T, find everything that falls in the range from x1 to x2. That's the interval we're looking for. And the first thing we want to do is find this split node. So there's 2 phases to the algorithm. One is going here, and then the other is walking down the left and the right chains. So I claim that this code, these couple of lines, will find the split node, which is the first node as we walk down the tree where there's interesting elements on both the left and the right side. So all this is saying is start at the root, and at each step I'll either go left or right until either I hit a leaf or I discover that there are interesting elements in both the left and the right-hand side. So that's just what this is saying. Okay, if my right endpoint of the query interval is to the left of the key value at this node, let's see, that would be like here. So the right end of the interval is somewhere over to the left. Well, then there's no one interesting in the right-hand side. Okay, so I can go left. And that's what it says. If there's no one, if everything's in the left-hand side, I'd go left. All right. Not very exciting. Now we have the split node, W. I'm not going to change W. There's one trivial case, which is if W is a leaf. Okay, if the split node is a leaf, then that means at most you care about only one node. Okay, so we just check whether that one node falls in the particular range we care about. If it does, we output it. Otherwise, we're done. Okay, it's the otherwise case that I care about. And there are two halves to this phase. One is going down this left chain and finding all these trees that are hanging off the right-hand side. And the other is going down this right chain and finding all the trees that hang off the left-hand side. Okay, it's completely symmetric, so I'll only write down the code for one of them. So I'll do the left-hand side. Okay. So again, I'll be aligned. So I'm going to walk all the way down the tree until I find a leaf. And at each step of the way, there's only one direction I need to go, depending on whether there's anything interesting in the left subtree. Okay, if there is, that means if there's something interesting in the left subtree, like here, I know that I'm going to find stuff down in the left subtree. That means everything in the right subtree is in the answer, because I know I'm between x1 and x2. I'm going to output the right subtree. And furthermore, I'm going to go left. Okay, like in this case. Output the right subtree and now walk left. And if there's no one interesting in the left subtree, well, then I just go right. Don't have to output anything. Okay, that's like in these cases. Every time I visited one of these three nodes, I found there's actually nothing in these subtrees that I cared about. So I don't have to go down there, I just walk right. And eventually I'll find something that interests me. Okay, eventually you get all the way to the point where V is a leaf. And the last thing you do is output V if it's in the range. Okay, that's the end of the left traversal. Then you do the right traversal in exactly the same way. Again, you let v be w. You loop down until you find the v is a leaf. You check the opposite way that key v is less than or equal to x2. You either go right or left, exactly flipped. Okay, so you reverse the roles of left and right. And that's the algorithm. Okay, it was a little tedious. But now, maybe it's obvious. How many subtrees can there be in the output? This is the only step I care about. So how many trees could there be? Is this too easy or too hard? Yeah.
Log of k.
Log of k. Yeah, that's right. I was thinking of log of n, but you're right. It's actually log of k. So let's write down some analysis. Where should I put the analysis? Here. Okay, so the idea is that what's the running time of this algorithm? Similar question. So let's see, in the top step, we're just walking down the tree. And then in this step, we're continuing to walk down the tree. Okay, so the running time is just logarithmic. So in log n time, we find, as you said, ordered log k subtrees. I should maybe be a little bit careful and add 1 here. There's at least one subtree potentially. Okay, if k happens to be 1 or 0, I don't want to have to worry about this being too small, or this being 0. Okay. It's annoying because log of 1 is 0 and log of 0 is negative infinity. Okay, I want this to be at least 1. Why don't I write max, just to be careful. And these subtrees represent the answer to my range query in the sense that everything that's in the answer is a leaf in one of these subtrees, and everything that's a leaf in this subtree is in my answer. Okay, so that's exactly what I want. And so that's in log n time, very fast. If I want to list all of the elements, all of the leaves that are in these subtrees, that just takes log n plus k time. Okay, so to enumerate the answer, or let's just say list. It's k plus log n to write down k elements. And I can do all these things that I said I wanted to do. I could count, let's see. If I wanted to know whether there's any 1 in the answer, I can just tell that by whether there are any subtrees in the answer. I could, for example, just give you the first point that's in the answer, or the first 10 that fit on your screen. If I'm looking for restaurants and there are 1,000 that match my query, I'll only care about the first 10 because that's all I can show. So I can do that in order 10 plus log n time, okay, faster than k plus log n. If I wanted to count how many answers there were, how many points were in my range, could I do that using just these subtrees without looking at all the subtrees, looking inside all the subtrees? This also goes back to the last lecture. So I give you a list of subtrees that represent the answer. The number of leaves in the answer, the number of leaves in all these subtrees is the number of points in the answer. So how could I count how many leaves there are in each subtree? Yeah?
In each node, you maintain the number of leaves.
Right. Each node, you maintain the number of leaves. So data structure augmentation. Right? Exactly. We maintain subtree sizes in the last lecture. You can maintain the number of leaves in just the same way. And so then it just takes order log n time at most, because I find the subtrees. Each one has in its root the number of points that are in there, and I add them up. There's only logarithmically many of them. All right. That's one-dimensional range trees. So let's go to 2 dimensions. Then things become more interesting. Okay, so the idea with 2-dimensional range trees is we'll have a 1-dimensional range tree for the whole thing. Sorry. I'll call this the primary range tree. So this is just saying I'm going to take exactly what I had before. I know how to do one-dimensional range tree in terms of like x-coordinate. I'll do that for all the points in my point set. Okay, my point set x and y coordinates, I'll forget about y coordinates for now. Build exactly the structure. This, I think, is sort of a bizarre idea. Okay. So what can I do? I can do one-dimensional range queries. And that means in order log n time, I can find order log n subtrees that represent the answer for one dimension. Okay? So these are the points that have the correct x-coordinate. So if I have a bunch of points, and I want to find the ones that are in this rectangle, okay, those are the points I care about. This is my 2-dimensional range query. What I'm doing is just projecting onto the x dimension. And I'm saying now, well, I could find all the points in this big vertical slab between these 2 vertical lines. I can find the subtrees that represent them in order log n time. Okay, this is where we're using the trees, right? If I had arrays or something, well, if I were using interval trees, to find all of these points would take time, at least however many points there are in there. Okay, it would take at least order k time, where k is the total number of points in this vertical slab, not the number of points that I actually care about. So what we're getting from the range trees is I can spend only logarithmic time, independent of how many points are in here, and find this subtree representation of them. So this is like an implicit representation of the answer to the one-dimensional part. Okay, now I need to do the 2-dimensional part. So the question is, how do we find the points? Out of those points, how do we find the points that are in the right vertical range? So this is maybe tricky. Does anyone see how to do this? Yeah.
Could you do the 1D range on each of the subtree?
Do a 1D range search on each of the subtrees. Yeah, exactly. Now, how am I going to do that? So I want range trees that allow me to do range queries in terms of y. Yeah. Rebuild a new tree. Yeah, so build a tree at every node. Okay, so this is sort of like augmentation. I'm going to have several data structures going on. Okay, so the idea is every node in the primary tree so in the range tree that searches in terms of x also stores another range tree. So that means I'm going to have a lot of range trees lying around. So I'll call these range trees secondary. Okay, and they're going to be able to do range searches in terms of the y-coordinate. And they don't represent all the points, they represent the points in that subtree. Okay, so let's draw a picture corresponding to that. So I have this tree, just as I did before. That's the primary tree. I'm just going to erase part of it and leave the rest. I did all this searching. In the end, I found these subtrees that represent the answer. Okay, there they are. So in particular, in logarithmic time, I know the roots of each of these subtrees. And these subtrees have too many nodes in them. They have all the x matches. I only want the leaves in here that also match in terms of y-coordinate. So I'm going to follow each of these nodes stores a pointer to some other range tree of about the same size as this subtree. Okay, I'm trying to make these roughly the same size. So every node, I mean, this is just for the subtrees I've been looking at, but every node in the original tree has a pointer to another range tree structure. So there are n plus 1. I mean, for every node in the tree, there's another structure. There's a linear number of structures. Okay, it sounds like a lot of space. But let's not worry about space right now. How fast can we search? In each of these trees, I want to do the same kind of search. Okay, I'll walk down until I find a split node. Then I'll go left. I'll find subtrees in here. Something like this. In every one of these, I'm going to do this kind of branching range search. Okay, I'm just drawing a rough picture so you get the idea. The point is that these little subtrees in here are the ones that match both in terms of y-coordinate, because this structure is all in terms of y-coordinate, and they match an x-coordinate because this subtree contained points that only matched an x-coordinate. Okay, so that's the idea. Search in all of these. And the key thing is that there's only log n of these subtrees. So I don't have to do too many searches. So what's the total running time here? Log n squared, right? So to do a range query takes me log n squared time. Because for every of the log n subtrees, I have to do a search, and that takes at most log n time. Okay, maybe plus k if I want to write out the answers in the end, plus k. Okay, so for whatever the size of the answer is, depending on what kind of query I'm answering. Okay. Maybe the more interesting part, I mean, it's not so surprising that this works. What's nice is that it doesn't occupy too much space. So what is the space occupied by this data structure? I've got lots of data structures going on here. Got a linear number of structures. Each one could have potentially linear size. So it's at most n squared. I claim it's better than that. Any guesses? So the first person who answers only has to give the answer. The second person who answers has to give the reason why. Log n. N log n. Yeah, that sounds good. Yeah, that's the right answer. Do you know why? Or leave that to someone else? Good. Exactly. So why is it n log n? It's not linear, because there are a lot of structures around. I claim it's only n log n. And this is the cool part about 2D range trees. Okay, well, what takes the space? For each tree, the space is linear in the number of nodes that are in that subtree. Okay, so in my original one-dimensional structure, which is what this is a subset of, my original 1D tree, from every node, I have another tree that's of size proportional to that subtree. Now, what do I know? I know how many leaves there are. The number of leaves down here is n. Okay, that's the number of points I have. The question is, how many times is a particular leaf in a subtree? Or how many subtrees is a leaf in? I look at the subtrees from every node. So the number of subtrees that contain a particular leaf is log n. There's n leaves. Each one occurs in only log n subtrees. So the number of subtrees, or the number of secondary structures in particular, that contain a particular leaf is only log n. Okay? If you look at a leaf in this tree, you follow its root-to-leaf path. Well, it appears in the subtree rooted at this node, and the subtree rooted at this node, and the subtree rooted at this node, and so on. There's only log n nodes along that root-to-leaf path. Okay? And there's only n leaves. Okay, so that's the query bound and the space bound. We should maybe also think about preprocessing. So whenever you have this sort of static data structure where I give you some input that's not changing, preprocess the input to support fast queries in small space. You also have to worry about how much preprocessing time it took. And I think this is not quite obvious from this point, but it's only n log n. Okay? I haven't described exactly how to build this structure, but you build the initial 1D range tree. That just involves sorting and throwing them into a tree. That's n log n. Then you have to build all these auxiliary structures, but basically it takes time proportional to how much space you use. Okay, so it's not too costly. Okay, so that's the idea with 2D range trees. You get really fast queries, only log squared n time to find out how many answers there are. Again, you can augment your data structures to say how many leaves are there in every subtree. And immediately you get the size of the answer, and you can take the first k elements in the answer and so on in an additional k time. Okay, the last thing I want to say about range trees is what happens when you go to d dimensions. Okay, so this is sort of like guess the pattern. So think about if instead of being in 2 dimensions, I'm in d dimensions. What's the query time? You have an idea? Or? No? Yeah? Log n to the d plus k, right. So the idea is in each of these secondary trees, from every node in the secondary tree, I store a tertiary tree, okay, 3rd level. And I do a query in that. And I only have, each one costs log n time. And so that gives me log n to the 3 for 3 dimensions. Okay. The space, can someone guess the space bound? It's similar. So I'm going to have a lot more trees. But again, most of them will be small, so this won't increase my space factor, my space by too much. So, yeah?
It would be something like n times log of the log of n times log of n, all the way to we have d logs.
No. It's worse than that, I think. Wait. So basically, for the first level store, to store the primary tree just takes order n space. To store all the secondary trees takes order n log n space. And to store the tertiary trees takes n log n squared space. Maybe that's what you said. I'm not sure. You add all those up. The dominant term are the last level. So it's actually n log n to the d minus 1 power. Okay, because one dimension only takes linear space. So each time you add a dimension, you add on a log n factor. Okay? Let's see. I have a little bit more time, so I want to cover what I can about a different problem. Are there any questions about range trees before I go on? Preprocessing. Oh, that's a good question. Preprocessing, I will fill in because I haven't said exactly how to build these trees. The same sort of thing. It just takes time proportional to the space that you use. Okay. So these are not the best data structures for this problem. You can improve the query time by a log n factor for this term. So you can actually get log n to the d minus 1. That's tricky, so I won't talk about it. You can improve the space by a log n to the d minus 1 power. Okay, that's really tricky. And those are the best data structures known for this problem, and in a certain model, that's optimal, in fact. But this is pretty good. I'm just showing you something that's log n factor away from the best you can do. Okay, any questions about range trees? Good. So maybe one of the... It's a nice structure because it builds on what we know how to do, which is search trees. Instead of going into the nitty-gritty details of rotations and so on, it just uses them mostly as black boxes. Each node you have to do something with, but it's not too difficult. OK. Let's see. I want to talk about line segment intersection. So I'm skipping over some slides in the notes here. So this is maybe the next step up, right? With range trees, we just had a bunch of points. Line segment intersection, I have a bunch of line segments. Okay, maybe I should be consistent with the picture I have here. I'll just draw a simple diagram. Okay, maybe I have this set of line segments. All right, that's a very simple set of line segments. The question is, do any of them cross, like in this picture? Okay, so given n line segments in the plane, so we'll stick with 2 dimensions because that's easy to visualize. Does any pair of those line segments intersect? Okay, so what's a simple algorithm? This is straight up algorithms, okay? No more data structures for the rest of the lecture. Just give you n line segments. How do I find whether any of them intersect? Okay, suppose I give you a tool. If I give you 2 line segments, it's pretty easy to figure out whether they intersect. But now I give you n. Easy algorithm for doing this. Yeah? Go through each one and check it with every other one. Yeah, so that's n squared. I go through every pair. Check whether they cross. Okay? And what I want to tell you about is an algorithm that runs in n log n time. Okay, so a lot faster. Pretty close to linear time. Okay, this problem and this algorithm is in the text. Okay, so I won't be as formal about it because you can read about it there. So it's called a sweep line algorithm. And the idea is we're going to sweep a vertical line through the input. And this you will also see on your problem set. We'll sweep it from left to right. So the idea is that we're replacing, I have 2 dimensions here, x and y. I'm going to, sorry, this is y. I should know my coordinates here. This is x. I'm going to replace x with time. And imagine sweeping a line that's initially way over at negative infinity or somewhere near there. Eventually, it starts crossing these line segments. It always stays vertical, and it always moves from left to right. Okay, over time. I just keep going. Okay? Very simple idea, but very powerful. Okay, so what can I do as I sweep this line? What I care about the line segments. So what I'm going to look at are these intersections. Wherever this line crosses a line segment, wherever my sweep line crosses the line segment, I'm going to store that. Okay, as time progresses. So this is like a dynamic set. I want to maintain, this is the invariant of my algorithm. I'm going to maintain a dynamic set S of the segments, the line segments, that cross my sweep line. Okay, there's at most n of them at any time, and it changes as time goes on, which segments I'm crossing. And furthermore, I want that set to be ordered. Okay, line segments by themselves are not ordered. Okay, I can't say that this segment is less than or greater than this segment. Okay, but when I cross with a vertical line several segments, there's a natural order to these crossings, right? Top down. There's this vertical ordering. This intersection comes before this one, comes before this one. So I say that for this particular instant in time, this segment comes before this segment comes before this segment. Okay, why don't I label them? Let's call this A, B, C, D. So at this particular crossing, the order of segments is BCD. Okay, I don't have enough space, but squeeze it in down here. So the contents of my, BAC. The contents of my dynamic set here will be exactly those intersections in the order that they occur. So here it's just BA, here it's just A, here it's just A, here it's nothing. Okay, over here, it's a particular intersection where we lost C. So now it's just we lost A. So now it's just BC. Here it's just C. Here it's D and then C. Here, after the intersection, we get C and then D. Okay, and eventually we get nothing. Okay, so that's how my dynamic set will progress as time goes along. In particular, I want to keep it ordered by y-coordinate of the intersection. Okay. The question is, when does the order change? Okay, what I've described is this nice continuous process where the line goes smoothly from here over to here. But algorithms in computers are discrete. They do things, they do a finite number of things. They can't do a continuous sweeping. Okay? But I don't care about the continuous sweeping, right? From here to here, nothing changes. The intersection is just A. So I can just skip over that part. What I care about are these transitions between different sets of the segments that intersect the sweep line. Okay, I care when S changes. Now, it could change that there's new elements in the set, or it could change in the sense that the order changes. Okay, so I care about the orders changing. So for example, if I see a new segment, might be crossed. Okay, that's an event that I care about. It could be that an existing segment that I'm currently crossing terminates. I no longer cross it. Right, or it could be that the order changes instead of just which segments get crossed. And I claim the only time that the order changes in this picture is when two segments cross each other. Okay, as long as nothing's crossing, as long as no two segments cross, everything's just normal. We're inserting things into particular places in the set and then eventually removing them. The order never flips. Here, the order flipped between C and D. Okay, and I claim that's equivalent to two segments crossing. Okay, this is what we care about. This we understand. Okay, this is whenever you encounter a segment endpoint. Okay, when I hit a left endpoint, well, that's a new segment that I'm starting to cross. When I hit a right endpoint, that's when I no longer cross that segment. Okay, so that basically gives me the algorithm. So here's the idea. This says that the key endpoints, the key events that I care about, so these are called event points, meaning event points in time, okay, not points in space. I should be grammatically correct. It's plural. So what I know about are the segment endpoints. And so I can tell when these events happen and when new segments are crossed and when they aren't. I can just process these event points in order. So all I need to do is sort them. And I'm going from left to right, so I sort by x coordinate. And then I just loop through them. Okay, so I sort them once. That takes n log n time. And I'll just, for each one, it's either a left endpoint of a segment, or it's a right endpoint. Okay, in either case, all I need to do is maintain my set S and then detect intersections. Okay, so first thing I should do is if I'm reaching a left endpoint, well, that's a new segment that's being crossed here. D got added to this list from C to DC. Okay, so I'll just insert S into capital S, the set of segments that are currently intersected. And I want to check for some intersections. And here's the neat part. All I'm going to do is check for intersections between S and its neighbors. This is a key idea. The question is, why does that work? Why is that enough that I just check S against its neighbors? Okay, let me just write down the other case, which is symmetric. If you hit a right endpoint, you delete S from capital S. And then I'm going to check for different intersections. I'm going to check for intersection between what used to be the neighbors of S. Okay, we just removed S. But wherever we removed it, it had neighbors. Okay, it had two neighbors, the up neighbor and the down neighbor. And I'll check whether those two segments intersect. Okay, that's the algorithm. Okay, you can find the pseudocode in the text. Why does this work? The idea is, consider the, so I won't write down any text because I'm almost out of time. Consider the first intersection that actually occurs. So you sweep left to right. What is the leftmost crossing between two segments? Okay, call that X. Well, that crossing, all that happened when I went from this sweep line to this sweep line is I flipped the order between C and D. Okay? So that means, in particular, C and D were adjacent in the order because they came right next to each other, and now they're in the opposite order. So at some point, C and D were adjacent in the order. Okay, and I detect whenever the order changes, because no intersections have happened. So all that can happen are that you see left endpoints, you see right endpoints. Up till now. Now something different happens. So that means at some point before here, I realized C and D were next to each other. And what these checks are doing is that whenever two segments become next to each other, when I add an S, it now becomes adjacent to these two neighbors. When I remove S, these two neighbors were neighbors of S before. Now they're neighbors of each other. Whenever two segments become neighbors of each other, I check whether they intersect. I'll find all the intersections. Okay, that's a clever argument. I encourage you to read it in more detail in the text. How long does this algorithm take? So what should I use to store my dynamic set S? I won't bother you. You use red-black trees. Okay? Use your favorite balanced binary search tree structure. And then what's the running time? I guess I already gave it away also. The point is, each step here takes logarithmic time, because I'm just doing one insertion or deletion. Whole thing is n log n. Okay, so that's a fast algorithm for doing segment intersection. Again, this is optimal in an appropriate model. And that's all. So on Friday, you'll see convex hulls, which is another cool geometric problem. And then we'll go back to data structures.